Welcome to Lab Module number 4, X-ray diffraction for phase identification. In this lab module, we will be using X-ray diffraction as a technique to identify the crystal structure and phase of a material. We will combine the X-ray diffraction pattern information with a database of X-ray diffraction information from other materials, and we will demonstrate how to connect the X-ray diffraction information to the identification of the phase of the materials. X-ray diffraction, often referred to simply as XRD, is a powerful technique for both quantitative and qualitative analysis and characterization of materials. Actually, X-ray diffraction has been used for more than a century, and its uses continue to grow. Common uses of XRD are to identify the types of crystal phases present, the structural makeup of the phases, the types and degrees of crystallinity or amorphous content in a material, and phase fractions. We can extend the capabilities of XRD to measuring strains and residual stresses in a material, and it is very useful for accurate lattice spacing determinations in the materials. We can also use it to determine preferred orientations of the crystals within a material, often referred to as crystalline texture. In this lab module, we will be using XRD to identify the types of crystalline phases present in samples, and we will use that data in conjunction with a database to do phase identification. So before we delve into the details of performing X-ray diffraction, it's worthwhile to spend just a few minutes to further explain what we mean by phase identification. The term phase identification infers that we are not only going to determine the crystal structure of the material, but to suggest the chemical makeup of the material based on additional data extracted from the X-ray diffraction patterns. From an XRD pattern, we are able to identify the crystal structure of the material, but we are also able to extract the crystal lattice spacings of the material with sufficient accuracy that these lattice plane spacings, or D spacings, can be compared to the known values from previously measured material XRD patterns. The values of the D spacings combined with the crystal structure information can significantly reduce the possible materials that fit the D spacings of your unknown material. This allows the development of search and match routines to speed up phase identification, as there will be very few phases that have good matching between the D spacings of the sample in question and the D spacings previously measured for a very large number of materials. This is because the D spacings of the material, even with the same crystal structure, have a strong influence on the D spacings based on the chemistry of the material. As such, we are able to make very good correlations between the measured D spacings of our samples and the known D spacings of materials previously characterized by XRD. In other words, we can make use of an XRD database. Okay, now on to the topic of X-ray diffraction. X-rays are a form of electromagnetic radiation, with wavelengths on the order of the interatomic spacings of most crystals. Information regarding crystal structure and identification results from the ability of X-rays to diffract upon their interaction with materials. In describing X-ray diffraction, we often illustrate this as X-rays undergoing a reflection from atomic planes in the crystal. This is not accurate in terms of the true physics, but it's a helpful way to schematically illustrate the behavior. However, X-ray diffraction is truly a diffraction or scattering phenomena that is fully three-dimensional. It is much more complex than the simple reflection model that we schematically use to illustrate the process. Let's begin by explaining how we generate the X-ray beam that we're going to use in our X-ray diffractometer. An electron gun is used to generate an electron beam that is directed using an electrical potential towards a target material. The target material is a metal, typically copper, but other metals such as molybdenum, tungsten, iron, cobalt, and chrome can be used as target materials to generate X-rays of a very specific wavelength. The choice of the metal target composition determines the wavelength of the X-rays being produced. Often, the X-ray source is a tube that contains the electron gun and the target material inside of a vacuum tube. The electron gun is heated by passing electrical current through the filament, and when the filament is sufficiently hot, then the electrons in the filament can overcome the work function of the material and escape from the material surface. By applying a large electric field between this heated filament or cathode and the target or anode, we can accelerate the electrons towards the target. That electron beam is directed towards our target material, in this case copper again, and the copper has cooling water flowing through it to keep it from heating due to the electric current in the beam impinging on the target. We don't want the copper to melt when the electrons interact with it. When the electrons strike the target material, two types of X-rays are produced. The first type, referred to as continuum X-rays, are essentially a continually changing wavelength of X-rays. These X-rays are not of interest for this application because their wavelengths cover a wide range of values rather than a single monochromatic wavelength. The second type of X-rays produced are what are referred to as characteristic X-rays. These X-rays are associated with a very specific electron transition in the metal. In the case of copper, for example, the most common X-ray generated is from the copper K-alpha X-ray, a transition associated with electrons in from the electron beam interacting with an inner shell electron of copper, ejecting it out, and an outer shell electron falling into the ground state position. That change in energy is a quantized quantity, meaning the energy from that electron transition is a distinct energy associated with the energy levels of the electrons. And hence, the X-ray that's produced from that transition has a very specific energy and hence a very specific wavelength. It is this type of characteristic X-ray that we will be using in our X-ray diffractometer. The X-rays generated from the electron beam interaction with the copper target can emerge out of the copper, and by suitable design of the target and X-ray tube geometry, they can travel out of the tube through a window. Often the window is made of beryllium, which is a very low atomic number metal that allows the X-rays to pass through it without significant absorption. Since the X-rays leave the tube through an X-ray transparent window, essentially a port, they emerge out of the tube through the port and can be directed towards the sample that we're going to undergo X-ray diffraction. At this point, the X-ray beam is going to travel towards the sample and interact with the sample. And if the X-rays undergo strong diffraction with the sample, then an X-ray beam will be detected by an X-ray detector located in the forward scattering direction. We employ characteristic X-rays in the study of crystal structures within an XRD unit because the single wavelength nature of the characteristic X-rays allows us to control the occurrence of constructive or destructive interference between the X-rays and the crystal lattice of our sample. The conditions for constructive or destructive interference depend upon the wavelength of the X-rays, the path length that they will travel through the crystal and back out, and the angle of incidence and the angle of diffraction from the particular crystal planes of interest. Again, we often use the term reflection to describe the X-ray geometry of diffraction. In reality, the interaction of the X-rays with the crystalline lattice of the sample is a fully three-dimensional scattering event. However, mathematically, it's easier to describe it as a reflection event. The concept of constructively interfering waves of X-rays is such that the X-ray waves going into the sample will be in phase with the exiting X-rays from the diffraction event in the sample. After the scattering, destructive interference will occur when there's a non-integer path length difference between the X-rays that are traveling through the crystal. These conditions of constructive interference are summarized by Bragg's law, which states that n, an integer, times the wavelength of the X-rays, lambda, is equal to 2 times d sine theta, where d is the interatomic spacing between the crystalline planes of interest within the sample, and theta is the angle between the incident beam and the planes of atoms of interest. From the drawing, using simple geometry, one can see that the path length that the X-rays take along the lower red arrowed path is longer than the path the X-rays take for the upper red arrowed path. The difference in path length is d sine theta on the loading path, on the path leading up to the scattering event, and d sine theta along the path following the scattering event. The total path difference is then d sine theta times 2, or 2d sine theta. The total path length that the X-rays on the lower red path have to travel so that they would be in phase as they exit would need to be either lambda, the X-ray wavelength, or any integer multiple of it. So Bragg's law is really geometry, indicating that as long as the wavelength is an integer multiple of that distance 2d sine theta, then the waves will be in phase with respect to each other. And when they emerge out of the sample, they will have undergone constructive interference. D again corresponds to the specific interatomic planes of a given plane of interest, and we denote that plane using the Miller indices HKL. In a cubic crystal, for example, these planes could be the two parallel 100 faces of a cube, as an example. So the HKL set of planes would be the 100 planes. But as you rotate the crystal, you will have different orientations of the crystal that will bring different planes into an orientation that can satisfy Bragg's law. If the path length designated as 2d sine theta is an integer multiple of the wavelength for each different d spacing, then you will get constructive interference. In other words, it will only occur at a specific angle theta. If it is not an integer multiple of the wavelengths, then the X-rays will destructively interfere with one another, and no strong diffraction peak will occur. So the X-ray diffraction pattern is a map of orientations of the crystalline lattice of the sample that satisfy Bragg's law. In this lab, we will be using a specific technique of X-ray diffraction referred to as powder X-ray diffraction or powder XRD. We will use a powdered sample for the purpose of creating many small individual crystals so that on average, the X-ray beam interaction with the sample at every possible different orientation of the particular crystalline lattice. This allows us to get diffraction patterns from this interaction of the X-ray beam and the powder sample, such that the peak intensities represent the true potential for diffraction from that crystal, assuming you could sample an infinite number of orientations. So in a powder X-ray diffraction experiment, you have the greatest chance to avoid what we refer to as texture, meaning that we sample a material for which the orientation of crystals involved are not random. So a powder X-ray diffraction experiment allows us to sample a fully random distribution of orientations of a given crystal, and hence the truest measure of the intensity of the peaks associated with satisfying Bragg's law. Here we show the actual diffraction unit that we will be using in this lab experiment. The sample is fixed in a horizontal plane, and the X-ray source or the X-ray tube moves in a clockwise direction around what we refer to as the focusing circle, and the detector moves around that focusing circle in a counterclockwise direction. The X-ray tube emits an X-ray beam that impinges on the sample at some angle theta. And if we use the geometry previously described, then the detector is measuring that diffracted X-ray beam at an angle that would be equal to 2 theta. So when we collect the X-ray scattering data for the detector, we measure the peak intensity of the X-ray scattering out of the sample, diffracting to the detector. Since the detector is moving along an axis that's equivalent to 2 theta, we will plot the data as X-ray intensity on the y-axis and the detector position 2 theta on the x-axis. It's important to recognize the detector is moving along 2 theta because Bragg's law simply uses theta in the equation. So if we're going to apply Bragg's law, then we need to understand that we have to divide the detector angle of 2 theta by 2 to simply get the Bragg angle theta. The XRD pattern for every different crystal structure is a unique pattern of intensity of the peaks that will occur and their position on 2 theta. You can think of it as a fingerprint for the given crystal structure. Now the fingerprint will vary based on the interatomic spacing. So for example, different orthorhombic crystals that have different A, B, and C unit cell dimensions will produce peaks at different locations. But the general signature of the peaks in terms of their position relative to each other will be unique for each individual crystal structure or phase. Here again we're showing the photograph of the Pananalytical Expert X-ray diffractometer that we're using in this experiment. The photograph shows the entire unit with the doors closed, and the different diffractometer equipment is located inside behind those windows. We will show you the inner workings of the chamber next, but the first thing we want to do is to show you that in fact it is possible to visualize where the X-ray beam is going to hit the sample. Here we show you a specific sample that's used to image the X-ray beam. The sample is a surface coated with a fluorescent material that when the X-ray beam impinges on that fluorescent material, the material converts the X-ray energy into visible light. So we're going to turn off the light inside the unit and allow you to visually see the X-ray beam hitting the sample. In this case, the sample is also going to be rotating so that we can create the largest number of different orientations for our powder diffraction sample. On the left side is the X-ray beam source, and it has a set of what are referred to as masks that limit the width of the X-ray beam, and a motorized or fixed slit that allows us to limit the length of the beam in the horizontal direction. So with the mask and the slits, we can control the area that the beam is hitting the sample by a combination of different masks to control one direction, in and out of the field of view, and the other one a slit that can be varied so that the beam is limited in the horizontal direction. In the example we're showing here, the slit is fixed at a particular separation, but when the source is at a low angle, it produces a projected beam that has a very wide coverage of the sample. And as the source moves clockwise upward as theta increases, the orientation of the slits becomes less inclined and the beam effectively becomes narrower. We also have slits that control the detected beam going into our detector so as to minimize the non-Bragg type scattering that might occur. This allows us to limit the beam going into the detector to just the portion of the beam of interest. Here we show a photograph of this type of powder diffraction sample that we will be using in this lab experiment. Let's now demonstrate how the insertion of the sample takes place. The sample is a small puck of the powder that's mounted inside of a ring holder, and the ring holder is inserted into the bottom platform. It's aligned there, and then the bottom platform is raised to bring the sample up to the proper diffraction height. Remember, in Bragg's law, the geometry is defined for a sample at a very specific horizontal plane. If the sample were above or below that position, then the diffraction angles would be different than in the schematic diagram we show for Bragg's law. And so the design of the sample insertion shown here is specifically set up to achieve the sample at that diffraction plane so that we can properly relate the incoming beam, theta, to the diffraction angle, 2 theta. Now we will show you the functioning behavior of the entire system while collecting an X-ray diffraction pattern. Here we will show you the workings of the diffractometer itself. Again, on the left side is the X-ray source, the large chamber with the large gray cables connected to it. The large gray cables are water cooling cables that provide the cooling water to the X-ray target. In front of the X-ray source, the white apparatus with the black cable and gray connector is the device that controls the slit size and the mask size. That's going to limit the X-ray beam size hitting the sample. On the right side is the detector. You can see it's labeled accelerator. The detector moves in the counterclockwise direction, and the detector has in front of it a slit control that allows us to limit the width of the X-ray beam that's going to enter the detector. At the start of data collection, both the X-ray source and the X-ray detector will move down to close to horizontal position. This is where theta is a relatively small angle to start, in this case 10 degrees, and the detector is located at the equivalent 10 degrees above horizontal in the opposite direction, which we define as being 2 theta or 20 degrees. So when theta is 10 degrees, 2 theta is 20 degrees. Then as the source rotates clockwise upward during the X-ray measurement, the detector will rotate counterclockwise upward, so they maintain that relationship between theta and 2 theta between their positions. We will show you the working of the detector and source now. Now we will show you the display of the front panel of the XRD unit to show you the changing positions of theta and 2 theta. The display also shows you the X-ray beam is turned on at an accelerating voltage of 45 kV. That again is the electrical potential between the cathode, the wire tungsten filament, and the copper target or anode. The current running through the filament is shown here as 40 milliamps. The combination of the accelerating voltage and the filament current define the number of X-rays being produced. The front panel display shows the initial theta and 2 theta positions, and as the data is being collected, you see how the two of them are related by a factor of 2. Next, we will show you the evolution of the collected X-ray diffraction pattern. The plot being shown is the X-ray intensity on the y-axis and the value of the detector position 2 theta on the x-axis. You note that initially there is a background that appears to be a high background, but is really only a few hundred counts. That's the background level of X-rays being measured by the detector, some contribution from electrical noise and some from non-Bragg scattering. As the detector and source move through the theta-2 theta combination of positions, each time the position theta satisfies Bragg's law, then the detector will detect a highly constructively interfered X-ray beam following the diffraction or scattering event, and a peak is formed. So you will see peaks arise each time we satisfy. Since the relationship in Bragg's law is between the wavelength lambda, the d-spacings of the crystal, and the value of the diffraction angle theta, we can use the measurement of the values of 2 theta to extract theta. Since the wavelength is known, lambda of K alpha for copper, then we can solve Bragg's equation for the d-spacing associated with each peak position. In this experiment, you're being asked to do phase identification for 7 unknown samples. We have collected the actual diffraction patterns for these 7 unknown samples and have provided them through the Canvas files folder for lab experiment number 4. We know that these samples are all metal oxides, and their commonality is that they're all metal oxides that happen to be white in color. This may be helpful information as the color of the material is also related to its composition. But I have chosen oxides of the same color to make the phase identification process more challenging. We're providing a small database of the corresponding d-spacings of approximately 40 known oxides. Your assignment is to use the collected X-ray diffraction patterns to identify the d-spacings of the peaks in the patterns for each sample. Then create your own matching routine using the data in the Excel file of the database and the peak positions that you determine for each sample's X-ray diffraction pattern. Since there will not be an exact match, as no two experiments are ever identical, what I'm expecting you to do is to allow for some small variation or difference between the measured pattern and the data in the database, and determine which sample in the database most closely matches the d-spacings for your sample. Now that the data is finished being collected here, you can see a pattern of the X-ray peak intensities on the y-axis and the 2 theta values where the detector was located on the x-axis. Each peak represents a condition where we've satisfied Bragg's law, which means that each peak can be used to calculate the corresponding d-spacings of a particular set of planes in the crystal. Your task is to identify the d-spacings for at least the first 10 peaks in each pattern. Then use those d-spacings along with the database of oxides and their corresponding d-spacings that we've provided and determine which material, in terms of which metal oxide, is associated with each of the 7 unknown samples. As a thought experiment, we have one additional task for you. 3 diffraction patterns are given here that were supposedly collected from sample number 7. These are labeled as sample 7, sample 7A, and sample 7B. Assume an experimentalist who is new to the task at hand was asked to prepare these samples for XRD and prepared 3 samples indicated as samples 7, 7A, and 7B. These 3 samples that are either the same material or due to some handling errors, since they are all white powders, they could either be poorly prepared samples of the same material or well-prepared samples of different materials. What we're interested in having you do is to determine which is true. If they were poorly prepared samples of the same material, explain what in the sample preparation could lead to the patterns not being identical. If the samples are actually identical materials, in other words, if the same material in each of the 3 samples, then their d-spacing should all come out to be the same. You will note in the patterns that the d-spacings calculated from each of those samples are not consistent. I'm looking for you to try to explain whether they are from the same material or from different materials. Again, all the samples are white powders, so it's easy that they could have been confused in their labeling. If you think they're from the same material, provide an explanation, and if possible, a calculation to show how the peak positions would be different based on some type of experimental error. If you believe these are in fact just mislabeled samples of different materials, then using the database provided Again, identify the phase present. Use a separate appendix to detail your search match strategy. In addition, use a special appendix to detail your discussion and analysis of samples 7, 7A, and 7B. This special appendix will be treated as a 20-point extra credit opportunity. The end. Good luck.